Let's run the cross-entropy method on a less contrived example. Just as in last week's assignment, we consider an insurer's risk reserve process R of T. The insurer starts with some amount of capital reserves, R0, collects premiums at a constant rate P over time, and pays out claims which arrive according to a Poisson process and have log-normal claim sizes. We'll look at estimating the probability that the insurer is ruined by their first claim. The first claim arrives at the time t1, which is an exponential random variable, and the first claim size is u1. The reserve after the first claim arrives is R of t sub 1, is then the initial reserve R0 plus any premiums gathered until time t1, subtract away the log-normal claim size u1. The CE method will allow us to find a good proposal distribution when we consider important sampling estimators that modify the arrival rate lambda and the claim size parameter mu. We code in the constants for the problem we're solving. First, we'll try to solve this just using Crude Monte Carlo. This is a copy of the parallel code we considered just before. The main simulation function is simulate batch, which counts the number of rare events which occur in a batch of 1 million samples. There you can see that we simulate the exponential claim arrival times t1, the log-normal claim size is u1, and the reserve after paying the first claim, r sub t1. We return the number of times this value is negative, corresponding to a bankruptcy of our insurance company. After a long pause, we see that running 10 to the power of 10 simulations only resulted in 7 simulations, which corresponds to bankruptcy. Thus, the order of the rare event probability is around 10 to the power of minus 10. Our confidence interval is quite wide because we didn't observe enough of the rare events. We can do better with the cross-entropy method. In each CE iteration, we'll simulate 10 to the power of 5 replications and take the best 25% of them to be our elite sample. The original distribution parameters lambda and mu are stored in the u vector, and the proposal distribution parameters are stored in the v vector. In each iteration, we simulate the arrival times, claim sizes, and calculate the reserves using the v parameters. Our intermediate goal, gamma I, is calculated as the 25% quantile. Note that we use the rho quantile and not the 1 minus rho quantile as before, because we are looking at a rare left tail event here, whereas above we looked at a rare right tail event. We find the elite samples and pull out the arrival times and claim sizes for these elites. For the elites, we calculate their likelihood ratios. A couple of strange looking things are happening here. Since the SciPy stats library doesn't parameterize their log-normal distribution in the traditional way, I found it simpler to just take the logarithm of the claim sizes and calculate the likelihood ratio based on these logarithms being normally distributed. Secondly, the likelihood ratio is calculated by taking one term and dividing by another, then multiplying by the third and dividing by the fourth. This is to try to avoid numerical errors. When numbers get too small or too big in any computer, they eventually lose accuracy, and this is just a consequence of the way that floating point numbers are encoded in binary. It'd be even more accurate to calculate the logarithm of the PDF values and add and subtract these. Finally, we calculate the weighted maximum likelihood estimates for the lambda and mu parameters using the elite samples and their likelihood ratios. These are stored in the v-vector and the iterations continue. Looking at the result, we see that the CE method has increased our lambda value from 0.1 up to around 8,000, and it also increased the mu parameter from 0.01 to 0.05. This means that the proposal distribution will have claims that arrive artificially quickly, and the claim sizes will be artificially larger, both of which will lead to seeing the rare event more frequently. The proposal distribution is useless by itself, so let's run an importance sampling estimate with it. Taking just 1,000,000 samples, we find the simulations which lead to ruin, and for those samples we calculate the likelihood ratios. This is one final optimization, as calculating the likelihood ratios for all samples is wasteful, as these numbers are just multiplied by 0 in the non-ruin simulations. The final estimate is that the ruin occurs with probability 6.3 by 10 to the minus 10, with a confidence interval in the order of 10 to the minus 12.